Well, again, Curtis, thank you very much for that. And now, since we can be sure that no one will ever ask that question again, please help me welcome our speaker for the morning, Dr. Abby Biswas, Group Supervisor at JPL's Optical Communications System. He is deeply engaged in NASA's Deep Space Optical Communications project called DSOC. And I've asked him to join us today because he is the person most responsible for preparing the Hale telescope for its role as a ground receiving station in the upcoming DSOC demonstration mission. Dr. Biswas received his bachelor's degree in metallurgical engineering from the Indian Institute of Technology. I'm going to miss the pronunciation. Kagwapur, I've got that wrong. In 1977, he earned his PhD in molecular science and materials science from Southern Illinois University, Carbondale in 1986. Having joined the research staff at JPL in April 1990, Dr. Biswas has more than 30 years researching and implementing optical communication systems and related technologies. According to one count, he has authored or co-authored more than 120 research articles, conference proceedings, and other publications. Dr. Abby Biswas, welcome to the Greenway Talks online at Palomar Observatory, and thank you for taking the time to speak with us today. We'll take questions at the end of the presentation. And for that reason, right now, I'll ask everyone to turn off their microphones. And with that, Dr. Biswas, please, the floor is yours.
The outline of my talk today is going to be a brief introduction of optical communications with lasers. And then I'll go into describing what deep space optical communications or DSOC is. And then I'll talk a little bit about the technologies the new technologies which we're going to test as a part of DSOC, including both the flight and the ground. And then with that, I'll summarize. So why optical communications? Also, I just want to remind you that throughout this talk, I'll use optical communications, laser communications, and laser comm interchangeably. They all mean the same thing. So historically, if you look at telecommunications from space, the wavelengths have been, the frequencies have been decreasing. The frequencies have been, that's typo. The frequencies have been increasing and the wavelengths have been decreasing. And the reason for that, of course, is that as you go to shorter and shorter wavelengths, you get narrower beam widths. And with narrower beam widths, you get higher power density at the target. So traditionally, you can see in the electromagnetic spectrum, X-band has been the workhorse for telecommunications in the past few years. K-band has also been flown. But now we're migrating to much higher frequencies with lasers, which are in the near infrared. They're in the close to about 287 terahertz. And so you can see that that's a few orders of magnitude increase in frequency. And what that does for you is it narrows the beam down tremendously. So if you look at this example of a X-band transmitted from Jupiter distances to Earth, it's several Earth diameters by the time it gets to Earth, whereas a laser beam from the same distance would be only about the size of the state of California. So you can see there's a tremendous increase in power density that you can deliver with the directionality of a laser beam. And this is just an example that shows the increase in data rate you could get from 180 kilobits per second to 2.5 megabits per second. That's a substantial increase. And so NASA wants to, as a part of their exploration and science, we want to send humans to far distances, such as the moon and then to Mars. We want to use high resolution instruments, and all these require high data. At the same time, the radio frequency spectrum in the K band and X band region is in contention because there's commercial demand for it, there's military demand for it, so it's kind of squeezed. So given this scenario, it makes perfect sense to go to sort of unregulated bandwidth, which is the optical frequencies. And what kind of capabilities do you expect from going to optical? So you must have all recently heard about the excitement created by the Mars helicopter. We actually have a bot that's flying around on the surface of Mars. Imagine that while this thing was flying, you sitting at your computer could see streaming imagery coming from that helicopter. This capability would become possible if we had optical links running from the helicopter to the rover and optical links running from the rover to the orbiter and all the way back to Earth. Of course, that is going to be a while before we get that smart. Another enticing thing about communications is light science. I've drawn a little cartoon over here that shows two spacecraft exchanging laser beams. With this, you can do occultation studies for a planetary atmosphere. You can do ranging studies, and you can use that ranging to get information about the gravity of that planet, or you can use it for other scientific purposes, including interferometry. I don't know if you are familiar with a mission that JPL flew called Grace Follow-On. They had actually optical interferometry between two spacecraft to monitor the gravity of Earth. And then finally, of course, there's human exploration, which everybody is getting ready for, and that also needs a lot of data to be exchanged, and optical communications would kind of enable that. So I'm not going to read through all the prospects of laser communications. There's several. I've talked a little bit about them, but there are consequences also of going to laser comm. It's not all an easy street. There's the noise problem. With laser communications, you're dealing with quantum noise versus in radio frequencies, you're dealing with thermal or Gaussian noise, and quantum noise obviously is much higher than Gaussian noise. So there's a penalty there. Laser beams that we're using are obstructed by clouds, and they also are affected by atmospheric sea, much more than radio beams are. There's also other issues like a lack of ground infrastructure, and that's why the opportunity that we have to use the Hale telescope is a tremendous one. And then there's technology maturation. We don't have a whole lot of experience flying lasers and sensitive detectors in space, and part of the DSOC's purpose for testing this is to retire the risk of deploying such systems. So to give you a little bit of background, NASA has started the laser comm in this decade. We've done demonstrations from lunar orbiter. We've done demonstrations from the space station. We are getting ready to do a relay demonstration where we can send data from Earth up to a geostationary satellite and relay it back down to another location on Earth. And then an extension of that would be to include a node in low Earth orbit, so we can do a network, from Earth to GEO to LEO. And then you may have heard of Artemis 2, which is supposed to launch in 2023, and that's going to be the first crewed mission on the Orion spacecraft that's going to go and do a sortie around the moon and come back. And that too will be using optical communications. It's not part of the mission telecommunications, but it will be used for exchanging data and video and all from the astronauts. So NASA already has established, at least at the demonstration level, several missions. Now, I've drawn a table here where there's a red box around DSOC. So if you look at the distances for all the missions, they're all, small fractions of an astronomical unit, an astronomical unit being the distance between Earth and Sun. Whereas you see that DSOC, we're trying to go out to 2.5 AU, which is beyond almost to the farthest distance of Mars. And you can also see that the data rates are on this yellow column. We're still trying to do 133 megabits per second from deep space. We can't do that from 2.5 AU, but we'll do it from closer distances. So that's a big differentiator of DSOC from everything that's happened so far, even though we have upcoming missions that are going to do 200 gigabits per second from LEO. So that's the big differentiator about DSOC. So we can define something called link difficulty. It's the product of the data rate times the distance in astronomical units squared. And if you look at all the things that I showed in the previous slide on the table, DSOC is at least 1,000 times more difficult than links to the moon. And so we have to overcome this difficulty gap. That's really what the DSOC technology demonstration is all about. How do we overcome this difficulty gap? And obviously the solution to that is using technologies. The technologies that are being used for all these near-Earth lunar kind of links are not good enough for doing deep space. So in this talk now, I will give you an idea of what the DSOC technology demonstration is, what the new technologies are, and then I'll just end up with the status of DSOC, where it is today. So DSOC is hosted by a discovery mission called the Psyche mission. The Psyche mission is selected by Discovery to explore this Psyche 16 asteroid. It will be launched in the August of 2022. And you can see on the right graphic here is shown the trajectory of the Psyche spacecraft. Now, Psyche spacecraft has offered to host this DSOC flight subsystem so that we can then use this opportunity to communicate back to Earth as the spacecraft moves away from Earth. Now, on the graphic on the right, you can see these little blue dots that are shown. So our baseline mission that's funded and that's been agreed upon are these blue dots would be opportunities that we could send our laser signal from the spacecraft back to Earth and try to close a communications link. After the first year of cruise, depending on how things work, we may have extended mission, but there would be a gap because the spacecraft goes into the daytime sky and you can't use Palomar in the daytime sky. So we'd have to wait for several months before it comes back into the nighttime sky. So here's an operational view of DSOC. There's 3 nodes. There's a node in space, which is what we call the flight laser transceiver. It's a 22 centimeter diameter telescope, basically, but it's a telescope that both transmits and receives, and it's sending about 4 watts of laser power at 1550 nanometer downlink wavelength. Then you have ground laser transmitter, which is a 1 meter telescope. It's here near Wrightwood, California. This telescope would transmit a laser beam up to the spacecraft. And that actually serves as a pointing reference. And using that beacon as a pointing reference, the spacecraft can now send the laser beam down to the Hale telescope, the 5 meter diameter Hale telescope. So this is a beacon-assisted, we call this a beacon-assisted architecture. All the optical comm missions that have flown even in near Earth so far have all been beacon-assisted. Because as you'll see, pointing of a laser beam is one of the big challenges of optical comm. And then the other nodes that are in this operational view, you have operational centers, and you, of course, have the Deep Space Network. The Deep Space Network uses the X-band to do its primary telecommunications to the Psyche mission. I mean, we are just a demonstration. The Psyche mission doesn't rely on our optical link because we're just doing this to test it. The Psyche mission relies on the X-band link that goes up from deep space. So I've got a telecom equation written there. You can read it or ignore it. I don't want to, task you with math. But basically what you have is you have a laser shown in this graphic. It puts out a certain average power at 1550 nanometers, which is in the near infrared. It's coupled by an optical fiber to a transceiver, which is the transmit receive telescope that I mentioned, which is a 22 centimeter diameter. And so the optics inside this telescope condition the beam so that when it comes out, when the beam exits, it exits with a beam divergence of 15 microradians, which is very, very narrow. And this beam, of course, propagates to Earth. And if you look at the graphic on the right, it shows that the beam intensity that's going out follows, it can be approximated by a sort of a Gaussian distribution. So you have a certain average power that's being transmitted with a certain width, and it goes through space. And of course, as it goes through space, it loses, there's a loss which goes as 1 over r squared. And that's the big loss that differentiates deep space from all the other optical comms that you see. So one way of looking at this is that when you're at closer distances, you can use laser beams at very high bandwidth. As you go farther and farther, you sacrifice the bandwidth and you gain what we call photon efficiency. And in the next few charts, I hope to explain to you what we mean by photon efficiency. So it's a trade of bandwidth versus photon efficiency. So this beam that goes out, it reaches the ground, and as I mentioned, it has this Gaussian distribution. So if you look at this contour plot here on the right, it shows you from 1 AU, the irradiance distribution that DSOC will transmit. And of course, we don't expect our pointing to be perfect. So the Hale telescope is shown by that tiny little icon over there, which is, we allow for a certain amount of mispointing. So in this case, we expect to be somewhere in this range where the irradiance is about 4 times 10 to the minus 13 watts per meter squared, which is a very, very faint signal, as you can well imagine. And the way we deal with this very faint signal is we resort to photon counting detectors. That's why you'll see that the key instrumentation that we bring to the Palomar telescope is this very, very sensitive and temporarily very agile photon counting detectors. And at the beam footprint, you can see by the time it gets to Earth from 1 AU is about 2,000 kilometers. And the Palomar sees this tiny, tiny 5-meter portion of that beam. And of course, the 200-inch telescope was chosen because given the logistics of doing this demonstration, we don't have the budgets to build any new infrastructure for this. So given the existing infrastructure, given that we have a 1-meter transmitter in Southern California, this was the obvious choice. So, like I said, this is a beacon-based architecture, which means that the first thing that one has to do is to do what we call link acquisition. And that link acquisition is done by sending a laser beam from the 1-meter telescope up to illuminate the spacecraft. And of course, this beam is not as narrow as the beam that's transmitted from space, the reason being that it has to go through atmospheric turbulence. If you made it a very narrow beam, the atmosphere would broaden it anyway. So so it's a broader beam. And so what that does is it drives the power up. That's why at the farthest distance of the spacecraft, we'll be transmitting 5 to 7 kilowatts of laser power. But when we start out and it's pretty close, then we'll just be transmitting hundreds of watts. So the three-step process is comprised of transmitting the laser beam, and then the second step, the spacecraft also points towards Earth. So the Psyche mission is cooperating with us. They will point their telescope to where they think the ground station is. And you can see in this cartoon that I have drawn here, there's this blue patch, which is the spacecraft pointing control. So they have a control uncertainty. Within that patch, there's a knowledge uncertainty. And what DSOC does then, it scans out this knowledge uncertainty, and we expect to be able to find the beacon somewhere in that patch. Now, if we want to search out the whole control uncertainty, we have the ability to do that. We have the field of regard to do that as well. So we search this out, and once this beacon is detected, then we lock onto it, which means that, I'll go to it right on the next chart here. Now here I'm going to show you 2 quick movies. This one movie shows a beacon. It's just an animation. of a beacon being transmitted from Earth as the spacecraft is getting farther and farther away. You can see the little green spot returns the beacon. You can see it's fluctuating because it will be fluctuating due to atmospherics. And then in addition to this, also this thing, there's base disturbance from the spacecraft. So the image would probably look something like that if we did nothing. But we have some technologies by which we stabilize our line of sight, which means we isolate ourselves from the base disturbance. And so once we stabilize our line of sight, we have very sensitive photon counting detectors that then see these photons and can count photons. And we use that signal to feed actuators that then maintain our line of sight. So it's called stabilizing our line of sight. Once our line of sight is stabilized, we can then then you can imagine that this telescope is now pointed, it's steady, and now we can start transmitting the downlink. So in this cartoon that's shown on the right, you can see that the beacon goes up, which is the green line. It hits the sensor, and then once the sensor is stabilized, we have the transmit beam, which is the orange line that bounces off a actuated mirror. And this mirror can be actuated so we can actually dial in what we call a point-ahead angle. And because of the long lifetimes, you can see that when the beam is transmitted from space, Earth is, the place where you're seeing the beacon, it's not going to be there. It's just like skeet shooting. You have to point the laser beam ahead of where you see the beacon from. And that's this angle that's shown here, which is the point-ahead angle. This point-ahead angle is many, many beam widths. It's about 20 or more beam widths. So if you don't point ahead properly, you can completely miss the state of California. You could be pointing somewhere out in the Pacific or Texas or somewhere very, very easily if you're not careful. So dialing in this point-ahead angle and pointing precisely so that the beam comes and overlaps Palomar is one of the big challenges of DSOC. So with that brief introduction, I'm going to give you now a sort of a functional block diagram of what the flight terminal has to do. So we have this telescope, which is this 22 centimeter telescope. It has to have this point-ahead mirror, which is a tiny little mirror. It's actually, I'll show you kind of what it looks like. So this point-ahead mirror is there. You have the laser transmitter, which sends the light beam over a fiber that then comes into a collimator. This laser collimator couples the light into the telescope and sends it out. And then you have this photon counting camera, which detects the beacon and helps stabilize the line of sight. And remember that in order to isolate ourselves from base disturbance, we have this isolation pointing assembly, which has actuators and sensors, which allows us to both separate ourselves, isolate ourselves from the base disturbance, as well as to do some pointing over some fraction of a degree, which is enough to cover the uncertainty of the spacecraft pointing. And then, of course, there's electronics and things like that. So many of the new technologies that are going to be on the flight system are the laser transmitter, the photon counting camera, and the isolation assembly. These are brand new. They've never been shown before. So far, I've talked about exchanging laser beams between space and ground as though they're just continuous laser beams, but we are doing communications. The laser beams are being turned on and off or modulated. And by doing this modulation, we not only are able to send communication signals, but other functions also are achieved. So first, I'm going to talk about the uplink signaling. In the uplink signaling, one of the things that we have to do is overcome atmospheric turbulence. We do, and I'll have a chart on that later. I won't go into it right now. But the signaling part of it is we modulate it as shown by these lines below. So there's two modes of modulation. One in which we have, if you can imagine, we have 4 time bins, and the laser can fire anywhere in the first or the second time bin, and the third and the fourth time bin, the laser never fires it. So those are always blanks. So that helps the camera on the spacecraft to synchronize its timing, because it knows that it gets these bins where the laser never fires. It helps to synchronize its timing. And then depending on which slot the laser beam actually appears in, you can send some data rates. You can send a very low data rate, about 1.8 kilobits. Another mode is if we want to squeeze out even more power when the spacecraft is the farthest distance, then we sacrifice this data rate. We don't send any data up, and we modulate with a higher duty cycle, just a 50% square wave. So those are the two modes in which the laser can operate. Now, if you look at these two so-called camera images on the photon counting camera, you remember coming from Earth, and Earth is pretty bright. Even though we do use a pretty narrow spectral filter, the Earth light still leaks through that filter. So if you looked at just the laser beam, you see the uplink plus Earth, which is shown by this blob over here. And so you really don't know where your beacon exactly is. And this is at a distance of about 2.7 AU. This is the farthest distance. At closer distances, of course, Earth is a bigger blur. But taking advantage of this modulation, you can do what we call up-down counting, so that you can basically do a background subtraction and pull out the beacon from this noise. And so you know exactly where your beacon is. And that allows you now to use that as a pointing reference. The downlink signaling is much more extensive. Now, this is where the photon efficiency part comes in. We've been working at JPL on this for a long time, and in the time that I have, and also my limited knowledge of information theory, I really am not going to go into try to explain this to you. I do have an excellent reference here by the people who invented this code, Bruce Morrison and John Hampkins, both at JPL. Bruce Morrison actually left JPL, but they did this work at JPL. And this is one of the enabling features of the signaling scheme. So the first part of the signaling scheme on the downlink is to use what we call pulse position modulation. So if you look at this graphic down below that shows all these little time slots. So in this case, you have 16 time slots, and then there's 4 time slots, which we call the guard slots, where the laser never fires. But based on which slot of these 16 slots the laser fires, and you encode either a 0 or a 4-bit word. So you can send 4 bits of information with one single laser pulse. And with the DSOC scheme, you can have 16, 32, 64, 128 slots. That means you can send 7 bits. And these slot widths are half, 1, 2, 4, or 8 nanoseconds. And then in addition to the data itself, you send a lot of redundant bits which help correct errors. And this error correction code that Bruce and John came up with is very powerful. Even if a third of the data symbols come across, you can almost reconstruct the entire signal from that. That's how powerful the code is. And the other noteworthy feature about this code is that it operates very close to channel capacity. Channel capacity is a theoretical limit of how much information you can pump through through a communications channel. And this coding and modulation scheme that we have allows us to operate within about 80% of the channel capacity, which is pretty good. Traditional codes usually operate around 50%. In addition to all that, we also have some other signaling tricks that we play. One of them is called interleaving. So what you do with interleaving is you jumble up the bits in space and send them down, so that if you have a long erasure, let's say you have a big erasure from pointing, because the pointing is going to be jittering. So this erasure, instead of taking up a whole serial row of bits, which would cause so if you're trying to send an image down, you can imagine a whole blob of this image would be missing. Instead, you jumble up the bits and then you reconstruct them on the ground, so that even when you have erasures, your image almost comes through. Most of the information on the image comes through. You still have errors, but you can get most of the information through. So that's the downlink signaling. And I think for DSOC, the 2 key objectives of DSOC is to prove that we can point from space and that this signaling can be implemented. So now I'm going to go into the technologies aspect starting with the flight system. So I said that the laser, because we have to fire these laser pulses in a very narrow time slot, instead of the laser being on continuously, you have a high peak power. So what we call these lasers, they have high peak to average power. For those of you who understand the propagation of laser beams and optical fibers, whenever you have high peak power, you get effects, parasitic effects, which could completely rob you of all the power. So you have to design this very carefully so that you don't hit that threshold where you can get these nonlinear optical effects. So all that was taken into account. This was a development done by a vendor called Kaki. And you can see a block diagram. I'm not going to go into the details, but it has a seed laser, which is just a very low power laser, which goes through an optical fiber. It goes into a first stage of amplification, which is a fiber amplifier, and then it goes to a second stage of amplification. So you start out with milliwatts here, and you're coming out with about 4 watts of average power. But depending on which pulse position modulation scheme you're using, the peak power can be 4, 32, 64, or 128 times. So that was that, and so this is a first of its kind laser. We built 2 of them actually. One is an engineering model, one is a flight. Both of them have been working quite well. The next technology that I mentioned was photon counting camera. This is based on Geiger mode avalanche photodiode array cameras. Cameras like this have been built and demonstrated on Earth, but the novelty of DSOC is that this is the first time we'll be flying such a camera in space. And this will allow us to detect our very, very weak beacon. The optical transceiver is also kind of, you can say, a pretty new technology. So here's kind of these are like early concept diagrams that we had when we were designing this. It's easier to explain how it works. So you can see we have this 22 centimeter off-axis parabola with a small secondary over here. So it comes to focus somewhere and it goes out. So you can both bring a beam in and couple it to this detector over here, or you have the transmit channel where a laser beam comes in and hits this fine steering mirror. This is the little point-ahead mirror that I was talking about. It's driven by piezo electrics, and so this mirror allows you to point the beam away from where the beacon is coming in. So the beacon is detected on a camera over here, and the transmit goes out. So we're transmitting 1550 nanometers, about 4 watts of that, and we're receiving 1064, very, very low amount of power. We're talking about hundreds of femtowatts of power. So you have this very bright laser beam going out at one wavelength and a very faint laser beam coming out at another wavelength. And this magical piece of glass here that we call a dichoic beam splitter separates the 2 wavelengths. But it separates in a way that the 1550 beam that's going out, there's a small portion of it that leaks through. Some fractions of a percent. And that light that leaks through, we can reroute it to our camera. So now what happens is on our camera, we have 2 spots. So we can look at the spot that's coming in, and we can also look at the spot that's leaving us. So you can see the relative position of those 2 spots. And then we can use our point-ahead mechanism to adjust the offset between those 2 spots to dial in the point-ahead. And this transceiver was built out of silicon carbide optics. So all these primary mirror, secondary mirror are all silicon carbide, but the small optics here are made of aluminum. And then finally, I'm not going to talk very much about this isolation pointing control system, but it's comprised of what we call these struts. These struts are actuators and sensors. Each strut has 2 degrees of freedom, so you can get 6 degrees of freedom, so you can orient your telescope to point it over the region of the spacecraft pointing uncertainty. And then in addition to the struts, you have launch locks for securing this thing during launch. And we also have something called a docking mechanism that's not shown in this sketch. But what the docking mechanism does, it stores the platform while we're not operating. So here's a family portrait of the flight subsystem. This pizza box size thing here on the left is the laser transmitter. Then you have the optical transceiver, which is shown here with the 22 centimeter mirror. This is the photon counting camera that's mounted behind this telescope over here. And this is, I haven't talked about the electronics. The electronics is using kind of legacy JPL telecom electronics because it reduces the risk, and that's all shown here. There's also electronics that's tucked underneath this transceiver. And because the way that Psyche spacecraft accommodates DSOC, it's half inside and half outside the spacecraft, the thermal problem becomes very challenging. So a thermal enclosure had to be built, which is shown here. It's called the DSOC accommodation kit. And so this is what would be actually bolted onto the spacecraft, and this transceiver sits inside this box. Okay, now I'm going to switch gears to the ground side of DSOC. as you can see, DSOC is a system. The ground and the flight are are sort of joined at the hip, because without a beacon, the flight system can't point. So the laser transmitter, we have this 1 meter telescope up near Wrightwood. It's actually run by JPL. In fact, my group operates this telescope. And so we've used it it's a dedicated optical comm telescope. And so for DSOC, we're going to use 10 500-watt lasers to get 5 kilowatts of average power going out. Now, the 10 lasers, this picture shown here, we do what's called multi-beaming. So we transmit each laser beam through a sub-aperture of the telescope. In this case, this was a 6-beam system that we had built before. The reason for that is, one is that you have redundancy. If you have one single source at 5 kilowatts and it goes bad, and high-power lasers do tend to be very finicky, then you've lost all your signals. But by having 10 of these, you have a lot of redundancy. If 1 or 2 of the lasers go bad, you still have most of the power to transmit. The other big reason for multi-beaming is, you can see in this plot over here, the blue represents a single beam going through atmospheric turbulence, whereas the red line represents 8 beams going through atmospheric turbulence. And this is a simulation, but we've actually verified the simulation with actual measurements. So you can see that when you have 8 incoherent beams going, then they average out, and all the intensity fluctuations become much smoother with the multi-beaming. So the multi-beaming serves multiple purposes. It gives us redundancy. It helps us to build up the power using lower individual power lasers, and finally, it gives us a more stable signal. So the Optical telescope is a Coude configuration shown here. It's got 7 mirrors, and then you have the optical bench down here. And you can see that we combine 10 lasers, and then combine them, and then bring them, and then transmit them at sub-apertures. This is a earlier picture of the laser assembly. Actually, we have this at Optical right now. It's got all 10 lasers mounted into a single rack. And obviously, this is quite it's a high power laser. It's quite challenging. You have to use very careful contamination control of the optics, because any dust settling on the optics will cause catastrophic damage, and so on. So there's a lot of things. And finally, of course, there's a very important laser safety aspect, and we've spent a lot of resources and energy making sure that when we transmit our high power lasers, that we will not inadvertently eliminate an aircraft or a space asset. But for the sake of time, I'm not going to go into any more detail about the laser safety. Finally, we come to the ground laser receiver and the Hale telescope. As I mentioned earlier, the Hale telescope was chosen because it affords us the large aperture, and also, it's easier because we're JPL and Caltech. That also, we have a relationship there, and also it's in the vicinity of our transmitter. So we did early trades on how exactly to mount our instrumentation into the Hale telescope. The 2 choices being the Cassegrain stage, or the Coude was also pointed out to us. And after we went through this trade, we determined that the Coude focus would best suit us, because the Coude focus was in less demand, and we could set up there and not have to mount it and dismount it every time. And then we have, in the Coude arrangement, you can mount all your optics on a bench, align it, and leave it there, and not have to, take it up to a cage and mount it up and make sure it's realigned every time. So I mentioned before that the key technology that we're bringing on the ground side is really, the lasers that I just mentioned, the high power lasers, are kind of pushing the technology some. But one of the key technologies are these superconducting nanowire single photon detectors. These were developed earlier jointly by NIST. Originally they were developed by the Russians, but in the United States, they were developed jointly by NIST and JPL. And JPL has advanced that technology quite a bit to where we have large size detectors, because you can imagine behind a 5-meter telescope, the detector size has to be, you can't have a 100 nanometer wire and expect to couple the light into it. So we've developed this 320 micron diameter detector. Now, these superconducting nanowires is exactly what they say. They're tungsten silicide wires that you can kind of weave, and when a photon hits this wire, it heats it up enough that for a short amount of time, it goes into a non-superconducting state. When it goes into a non-superconducting state, the current that was flowing through the wire now flows through a shunt circuit, and you get an electrical pulse out. So for every single photon that hits this wire array, you get one pulse out coming from that particular wire. In DSOC, we have 64 of these wires, and actually they're arranged in 4 quadrants, with each quadrant having 16 wires. And that arranging it as a quadrant also gives us the advantage that we can use that quadrant to help improve our pointing, because you can use a quad cell, the position of the spot on the quad cell, to drive actuators so that we keep our spot centered on the detector. So once you detect the single photons, you get these electrical pulses from the detector back end. And then also there's one big advantage of these photon counting detectors is that they have very low dark noise. So you don't get a whole lot of dark events, but you do get background events. In DSOC's case, we're operating mostly in the nighttime, but if we could operate on a full moon light where there'd be some background, so you'd get background counts. So in the earlier days, people thought of these COM receivers to have ADCs, where you'd have the analog signal come in and you do analog to digital conversion and you get these digital counts. What we did at JPL, we re-architected this to use something called the time to digital converter. The time to digital converter has 64 channels, one channel attached to each wire. And what these TDCs do, it's like a 1-bit ADC, if you like. So when a photon arrives, it fires and it gets a timestamp. But when there's no photons coming, it's just waiting for a photon to come. It's a much more efficient way of counting photons than having this ADC that's continuously running and putting out some digital signal. So these TDCs put out these timestamps. So what you get now is you get a bunch of timestamps coming out, and then these timestamps are then processed in these very high rate FPGA cards, and it goes through a number of different functions. First of all, the timing is pulled out and you do temporal synchronization. Then there's the decoding, the demodulation, and then finally you pull out the information that was originally sent from space. And that information is, of course, stored locally. So this what we call the ground signal processing assembly also is one of the first of its kind, using a photon counting system like this. And then we have the optics at GLR, which couples the light from the telescope to the detector. So this is just, this optics has many functions. One of them is it has an acquisition camera, so that initially we can make sure that the signal is being received. It has polarization control. It has closed loop control to keep the spot on the detector that I mentioned before. It also has a test simulus, so when we're not on sky, we can generate our own signal to test ourselves. And we've conducted a series of engineering night campaigns, and we're beginning to actually test this optics with the telescope in the next few months. So we have a fairly good understanding of how to track non-sidereal objects with the Hale telescope using the Coude path. So this is a cartoon of how we decided to accommodate ourselves in the Coude spectrograph room. We have a rail that's past the Coude slit here, and the light comes down, it's folded into our optics, and here's our cryostat with the superconducting nanowire detector that's at 1 Kelvin. And then we have all the instrument racks here, and here we have a compressor. This one thing about this cryostat, it doesn't use any consumables. We have a cryocompressor here that pumps liquid helium. It's a closed cycle pumping, so we don't need to bring helium up to the mountain. And so normally we keep this detector at about 4 Kelvin, and then when we're ready for operations, we charge it up, and it stays at 1 Kelvin for about 12 hours, which is more than sufficient for a single pass. So in the past month, we've actually managed to assemble all this in the Coude spectrograph room. Here's a photograph of that. Here's the cryostat. Here's the optical box. You can barely see the rail over there, but on this graphic on the right, you can see this is taken from here's the rail and here's the fold mirror that sends the light into the optics box. And then here we have all our racks with instrumentation, and they're thermally controlled racks, so we don't send any heat into the dome. And then there's chillers and everything. So this is very exciting. We are waiting our next opportunity to go on sky and see first flight on this detector. We were hoping to do that on the 18th of August, but the weather gods weathered us out. It was overcast all night, so we couldn't open the door. But September 17th is our next opportunity, and we're hoping to get favorable weather to get first flight here. Okay, so that now brings me to my summary. So the DSOC flight system, as we talked, has actually been integrated to the Psyche spacecraft. Unfortunately, there's not a released photograph of it yet, or at least I haven't been able to get a hold of it. So I can't show you a photograph, but if any of you go to JPL, you can go to the high bay too, and you can see it actually. And now we're awaiting the spacecraft level environmental testing, both thermal vac and vibe. The GLR, as I showed you in the photograph, it's fully assembled, but there's a lot of testing that's still coming up during the fall. We have to do all our verification testing, and then there's software that monitors and controls everything that has to be tested. And then we have to test all our external interfaces, over the network and so forth. The ground laser transmitter is also assembled. We have 8 of the 10 lasers operating. It's kind of a finicky system. But we're getting there. There's a lot of thermal management, contamination control, and laser safety testing that's going on. Our operational readiness review for the DSOC tech demonstration is in 2022. I'm just going to leave you with an enticing view. I mentioned earlier that one of the deficiencies of optical comm is ground infrastructure, and we've been struggling with that for a while. One of the concepts that JPL is pursuing is to put mirrors on our existing DSN antenna shown by that graphic there, and to use this as a receiver. You can get 8 meters of aperture. You can operate in the day and night. You can operate about as close as 10 to 12 degrees from the sun, at least conceptually. But we are going to deploy, I think, a first 7-segment mirror next spring to test this concept out. But with that, I'll leave you. Thank you so much for your patience and attention. Go Psyche, go DSOC. And I need to acknowledge the generous and unwavering support from our sponsors, our NASA sponsors. As you can see, this DSOC is sponsored by 3 directorates in NASA, by the JPL program offices and the division management. Caltech Optical Observatory's directorate and staff have been phenomenal. They've been, I don't have enough words to say how helpful they've been. The Psyche project and management team has been very supportive. And of course, as you can imagine, the DSOC team, including all our contractors, it's been a very, very, very exciting time for us. And here we are on the threshold of launch. Launch is less than 1 year away. And thank you very much. And finally, I want to thank all the audience. I mean, in the end of the day, you are the main customer of all this technology and science.
Dr. Biswas, thank you very much. That was a wonderful presentation. And if I may, I'd like to open the floor for questions.
Thank you.
Okay, I'll start with
yes,
one.
I have a question.
Okay. Go ahead.
What is the attenuation of the atmosphere from turbulence and from absorption, and how much could be gained by going to a space-based transceiver, maybe in low Earth orbit or at the Lagrange point?
Excellent question. So the attenuation itself, since we're operating at 15 nanometers, the attenuation isn't that bad. It's depending on the elevation angle, you can get away with less than 2 dB, which is almost like 70% transmission or more. We can do as well as we can do up to as well as 90% transmission if you're close to zenith. So the attenuation is the turbulence, of course, is a big factor, and that's one reason why for this deep space optical comm we use direct detection. Because with direct detection, what the turbulence, the main impact of the turbulence is to blur up the spot size. And that's why we need large enough detectors. I mean, for many of the near-Earth airports, they use adaptive optics and they take out all the atmospheric aberration. We don't have any signal source to do adaptive optics because our signal is so faint. If we split off any of it, we would be left with nothing to do the comm. So our effort is more brute force. We use large detectors with direct detection with photon counting. So that there is an atmospheric impact. But it's again fractions of a dB, and 1 dB means about 80%. So it's maybe 10 to 20% of penalty.
So it's not too bad. It's pretty good. It seems like that's not much
pretty
lost.
Good as long as the weather is clear. As long as the weather is clear. I mean, if we get anything other than optically thin clouds, then we're out. Then we're basically out.
Okay. Thank you.
Ken, you had a question.
Yeah, this is a great talk, by the way. Very well organized, and it covers so much. One question on the uplink transmission. You had two diagrams, two coding schemes. One was just a beacon only, and the other is the beacon with some uplink data. What sort of uplink data do you send? Is it part of the communications protocol to acknowledge receipt of transmission or something like that?
No, we're not using it for that. What you're asking is it an ARQ scheme? We could use it, but because we're a tech demo for the first time, people are very nervous that we'll send a command and there'll be an error in the command and it'll do some unexpected thing. But we do have the ability, for example, to send commands up where we could request retransmission of packets, or even more important than that, the value of the uplink data would be to, let's say we're seeing very weak signal on the ground, if we could command the pointing do a very long lifetime sort of closed loop pointing control. So we're toying with those ideas. They're not in the baseline currently, but hopefully, we'll be able to persuade people to allow us to use the uplink communications to do something useful. But right now, it's just a demonstration. It's just sending some pseudorandom data.
Oh, I see. So when you actually do the experiment with Psyche, how far away will the satellite be? Will it be all the way out to the asteroid belt? So in other words, fairly representative of Mars communications?
It will be fairly representative of Mars, but it won't be all the way out to the asteroid. The asteroid is actually more than 3 AU. It can even go as far as almost 3.7 AU. We are planning to operate out to 2.7 AU, which is about the farthest Mars distance.
Okay.
I have a question.
Yeah.
Maybe I missed it, but do you use a narrow band infrared filter at 1.55 microns? And if you do, what kind of bandwidth does it have? And do you have to worry about Doppler effects taking the signal outside of that bandwidth?
Excellent question. Yes, we do have to worry about Doppler effects, and we do have narrowband filters. So at Palomar, we have 1.3 nanometer 1550 filter, and we also have a 0.17 nanometer volume bragg gating filter. The reason why we have that bypass filter is most of the time we're going to be operating at night, and we get lower attenuation when we go through that wider filter. The very narrow filter, we also want to test it out, because if we were operating in the daytime sky, we would need that very narrow filter. So we have both. Those. I'm sorry, what did I miss some part of your question?
Well, especially with that narrower bandwidth, do you have to worry about the relative motions of the satellite and the Earth taking you outside of that bandwidth?
That limits how narrow you can make the filter. So the 0.17 nanometer filter just barely accommodates the Doppler shift within it. If we went any narrower than that, then we'd actually have to actively tune the filter. And we don't want to do that. At least not right now. Maybe in the future we can.
Thank you. My second question, if I may, is for your ground station, you got these 10 high-powered laser beams. If they are not perfectly in phase, they could interfere with each other at the satellite position. Beams could cancel each other out. How do you deal with that?
Yeah, we detune them. You have to detune them by like a gigahertz or something like that in frequency, and then they don't interfere with each other anymore. So the 10 lasers, they're all slightly detuned from each other.
Okay, thank you.
Yeah. And we also have a narrowband filter actually on the spacecraft side, but that's like 1.3 nanometers. That's much wider. And again, So we don't have to worry about the Doppler. It's all contained within that.
Thank you. Very nice.
Thank you.
So you're saying, I think, that the system is only hopefully going to work out to 2.7 AU, but surely if it works that far and you're getting good data, you'll try it all the way to Psyche, right?
Yeah, the only pause that I have about trying it all the way to Psyche is the beacon. I mean, we have to have a certain SNR of the beacon to stabilize our line of sight. And we do carry margin, and I think we should be able to make it out to 3 AU, but it depends. Like if the spacecraft is very low at very low elevation angles, then obviously we get more atmospheric turbulence effects on the beacon, and the signal becomes weaker. If the spacecraft is high in the sky at 3 AU or something, then I think our beacon will make it. Yes, I mean, those will be all extended mission questions. So if we operate well over our first year that's spoken for, it's early in the Psyche cruise, then I think there'll be a lot more believers and people will be more partial to turning us on for the rest of the mission. Right now there's a lot of skeptics out there. So, yeah.
Okay, thank you again.
Other questions, please? Other questions?
Yeah, hi. Thank you for the speech. This has been a very, very good lecture so far, sir. Much appreciated. I have two questions. One, you mentioned part of the break-in training period will be to assess how well we can track at the non-sidereal rate with the 200-inch. Do we have any experience of that in general?
Yeah, we've been tracking. Actually, we've been tracking Psyche, the asteroid, and then several other asteroids with the Coude flat. The Coude flat has some idiosyncrasies that we understand, and we have measures to deal with. So yes, we have tracked non-sidereal objects with
okay.
200 each.
Thank you. And my second question would be, once we're like 3-4 years down the road, if everything's working smoothly, roughly what percentage of the 200-inch time will be devoted to this mission?
Oh, that's a great question. So for our prime mission, which is the first year, I think we're typically, I mean, it's kind of, Psyche has to allocate us time in coordination with the DSM time and all that. And then we have to be between sunset and sunrise at Palomar. So it's quite a constraint problem. But right now we're talking about 55 to 60 opportunities in the first year. So in each semester, I think they're split like maybe 25 in one semester and 35 in the other semester. But if we go into extended mission, probably the cadence of our opportunities will be much less. Because we probably won't be trying to operate every other week or something. And the reason why we've scheduled so many opportunities that we're expecting that half of them will be weathered out.
Okay.
Because
perfect.
remember that for our demo, both Table Mountain and Palomar have to be clear. And so we're expecting that they're going to lose half the opportunities to weather.
Excellent. Thank you, sir.
Could I do like a follow-up on that? Do you foresee that the Hale telescope is going to have a role in DSOC beyond this initial demonstration mission to Psyche?
So right now there aren't any proposed or planned missions to deep space. But people are working on them. So if missions go out to Lagrange or to Earth leading orbits or to Mars, any of those, yes, there could definitely be a role, for Hale to play. I know our colleagues at Goddard were trying to use the Discovery Channel telescope in Arizona for one of their efforts, which actually didn't get selected. But yes, the answer is yes. I mean, as long as the COO is willing to accommodate us, we will, and if the Coude is not under high demand, we can take advantage of that setup.
Very good, thank you. And lately, Coude has not been up until this point. Coude has not been particularly in demand on the Hale telescope. Are there other questions? Anybody, please?
Yes, I have a question. Is there any advantage of using an intermediate satellite in Earth orbit to communicate with the more distant satellite, or would the double pointing to a ground station and the satellite pose too much of a logistics error?
No, that's actually an excellent question. I think there would be tremendous advantages of having an intermediate satellite. The trouble is the cost. I mean, NASA has looked at the cost of putting up an orbiting receiver, and it's just prohibitive. You know, and until we understand how our receivers work, how our communication systems work properly, it's just too high risk and too high cost. But I can imagine in time, long past my days, perhaps, that eventually it will make sense to put the receivers in space. You know, once we're the technologies for deploying, you know, mid-size apertures in space and all, it becomes routine, then that will make more sense. But in the meantime, I think we have to push from the ground.
Thank you.
Can I go back to the demonstration a minute? You said 55 to 60 opportunities, and probably half of them would be weathered out. What would be the time duration of a given demonstration opportunity? And then when you get into the more of an objective system, would you expect to communicate data, you know, at these data rates all night? Or would it take a fraction of a night for regular communications?
Yeah, thank you. That's an excellent question. So for DSOC, you know, Psyche is a solar electric propulsion bus, which means that they have to maintain a certain thrusting duty cycle for them to get to the destination. So they have some natural coast cycles. So during the coast cycles, whenever we have a contact, they give us the entire time, which could be from anywhere from 6 to 11 hours. They'll allow us. But there's a very few of those because most of the time they're thrusting, and when they're thrusting, they don't want us to interrupt their thrusting for more than 2 to 2.5 hours. So our minimum contact times will be 2 to 2.5 hours, and we will get maybe opportunities to do a full 8-hour contact. But there'll be like maybe a few of those when they're during their coast cycles. In a routine operational system, we would like to operate the link, over the entire duration of the pass. I mean, because we transmit high power lasers, we want to cut off the link at 20-degree elevation because the big laser safety issues crop up if you go to lower elevations. So from 20-degree to 20-degree, we would like to use the entire duration. But you bring up a very good point because if our links operate at the data rates that they do, we may exhaust the data source on the spacecraft because the data buses on the spacecraft and all are not keeping up with the rates that we'll operate at. So it's possible that we'll operate for much shorter time. So the amount of time that a mission will have to dedicate to telecom will get reduced and they can spend more time doing science.
Another question, because it got triggered by what you said, are there airspace deconfliction issues with the uplink laser? Yes.
So we have a direct data feed from the FAA, which gives us information on all transponder-bearing aircraft that are approaching our beam, and we also have our own suite of visible and IR sensors that look for aircraft that don't have transponders because there are many small private planes that fly without those. So between those two tiers, we interrupt that. And we've done testing with this. A typical aircraft flying through our beam is a 3 to 5 second interruption. So it's not a very big deal. We shutter the beam, and the aircraft flies through, and then we just release the shutter. We don't actually have to turn the lasers off.
Oh. Thank you.
Well, with that, Dr. Biswas, you've been very generous of your time. Thank you very much. Can I conclude with one general question? You described the background and the history of DSOC and previous missions. you've been working at JPL, working on this issue. I take it from what I read for 30 years. During all that time, could you identify one key technology breakthrough that has made DSOC possible?
Excellent question. Yeah, there's been several of those, but I think the superconducting nanowire detectors are by far I think that's the biggest technology breakthrough, especially to be able to get them into a size, sufficiently large size to put it behind large aperture telescopes. And the 300 micron size is not the limit. I mean, they're making millimeter size detectors in the next generation. Because these detectors are almost your ideal photon counter. You know, a photon comes, you get an electrical click out, very low dark noise, and they also have excellent temporal characteristics. If you notice, you know, our whole communication signaling scheme is based on knowing the time of arrival of the photons. That's really what encodes the data. And these detectors, they have a reset time of tens of nanoseconds. So they're very good timing devices. And, you know, I think that these detectors are going to play a role in astronomy, you know, for looking at, I don't know, optical emissions from pulsars or quasars. I'm not an astronomer, but I'm sure that they, you know, doing any kind of time, you know, any kind of spatio-temporal kind of spectroscopy or detection or imaging, these detectors will play a very big role in the future. They have a long way to go.
Well, thank you very much for that. And thank you very much for the presentation and for this discussion. There are no further questions or issues people want to raise. Let me conclude by mentioning our next Greenway talk on Saturday, September 11th. The Greenway Talks online will continue with a presentation by Dr. Mansi Kesaliwal, Professor of Astronomy at Caltech. Her research group uses 2 robotic wide-field infrared optical cameras.
Oh, yeah.
Infrared and optical cameras at Palomar Observatory to discover and characterize brilliant flashes of light that tell us about the life cycle of stars and their role in the chemical evolution of the universe. And Professor Kesaliwal has mentioned to me that an announcement will be coming out on September 9th, and we will have an opportunity to hear all about that. And lastly, but not leastly, that's not a word, is it? Last but not least, that's what I wanted to say. An important event that you should not miss takes place tomorrow afternoon, August 29th at 5 p.m. Pacific time. Timothy Thompson, Mount Wilson Observatory trustee, observatory docent, and session director, is continuing his monthly presentation series, Sundays with Tim, in which he chronicles the history and achievements of Mount Wilson Observatory. And he does so while sitting under the gaze of Dr. George Ellery Hale. You can obtain the Zoom link to this meeting on the Mount Wilson Observatory website. So, with that, thank you again, Dr. Abby Biswas, and my thanks as well to all of you for coming. Have a great Labor Day weekend, and we will see you in 2 weeks. Bye-bye.
Thank you. Thank you very much again, everybody.
Thank you.
Thank you.
Thank you. Bye-bye.
Great.